Hi students, it's Dr. Marks, and our topic for today is R-square and F-tests, two measures that we're going to use to describe our models. We're going to look at some basic measures that evaluate our regression models. R-square is one of them, and then the second is our F-test of overall significance. Both of these things can be evaluated from the information that comes from our statistical output. So if we're using Excel or we're using Stata or R, they're going to report for each of your models R-square and an F-test. Be clear that these aren't things that are specific to a variable like a coefficient and a t-statistic. These are for your model as a whole. But we need to be careful because neither definitively tell us if our model is good or not. For example, the R-square and the F-test aren't able to tell us that our model is correctly specified. Maybe I've not put together a very good model, but I could still have a reasonable R-square and I could still pass an F-test for overall significance. So these are good first evaluations, but we do need to be careful. We need to know what these measures do and do not tell us. Let's start with R-square, and you're going to see it written two different ways, R-square spelled out or R with the superscript there to make it squared. R-square is a goodness of fit measure, so we refer to R-squared as our goodness of fit. It's asking what percent of the variance in our dependent variable is explained by our set of explanatory variables. So let's think about this. All right, the first part says what percent of the variation or variance in our dependent variable. Second part is explained by our explanatory variables. All right, let's think about this. Now we have a dependent variable, right? It could be test scores, it could be GPA of students, it could be salary of workers. And we know there's going to be some variation. Not everyone has the same test score, not everyone has the same GPA, not everyone has the same salary. And our model is trying to explain why some people have high test scores or high salaries and other people have low test scores and low salaries. So we're trying to create a model that explains the variation in that dependent variable of interest. Well, hopefully we've put together a model that has useful explanatory variables that do a good job of explaining the variation in salary or test scores or GPA. That's what our R-square is measuring. In other words, how well does the model fit the observed data? And that's going to be really related to reflecting the strength of the relationship between our explanatory variables and our dependent variable. R-square is measured on a scale from 0 to 1. So when you look at your output, it's going to be expressed as a decimal. For example, you might do a regression and see that you have an R-square of 0.62. And what that means is that the model explains 62% of the variation in the dependent variable. So we tend to interpret R-square in percentages, but it's reported as a decimal. So don't let that confuse you. Now, this is all related to that idea that we've talked about before, which is we are trying to create a line of best fit that minimizes the squared residuals, right? Look at this blue line in each picture that's been fitted, and we see that not all of our observations, right, are going to fit the line. So here we're looking at our observed responses mapped against our fitted responses, and they don't all fit on the line. We have some error. Some of it's positive, right, because we're above the line, and some of it is negative because we're below the line. And if you recall, in the past we talked about wanting the squared error, the squared residuals, because we don't want to take +4 and add it to -4 because that adds to 0. That would make it seem like I have a perfect model. There's no residuals at all. Well, that's not true. I have +4 and -4. So if I square each, then I have 16 and 16, right? And then I can really get an idea of the magnitude of the sum of the residuals, taking into account that some are positive and some are negative. Now, if we look at the first picture on the left, we see we have a pretty good amount of residual, right? Both positive and negative. Well, we have an R-square in this model of 0.38. But on the right, we see that the line fits the data a lot better in terms of lower residuals, right? We're going to have a smaller sum of squared residuals. And we have an R-square of 0.87. So R-square is related to that idea that we've talked about before. So then to recap, R-square, as we just said, is related to the residuals. And it's important that you understand what we mean by that. And we've talked about this before. So how well does the data fit the regression line that we fitted? But as we just explained, we need to take the sum of the squared errors, right? Instead of positive 4 and negative 4 offsetting each other, we make it 4 squared and negative 4 squared, 16 plus 16. Because then we don't lose anything by positives offsetting negatives. Here's the equation for the R-square, and I don't want to intimidate you with this, and I'm not going to ask you to calculate it, but I do expect you to understand it. Let's look at the top part, which says R-square equals 1 minus the ratio between, in the numerator, the sum of the squared regression error divided by the sum of the squared total error. So let's dive into that by looking at it on the bottom, because this will make a little more sense. So in the numerator, our sum of squared regressions, we understand that, right? That's the sum of the squared errors. Think about what we're doing. Yi is an observation, so maybe it's test score for student I, student 1, for example, minus the predicted value. So once we take into account all the variables for that student, what would be the predicted test score? So we look at actual minus the predicted for student 1, square it, then actual minus predicted for student 2, square it, and I add all these together. On the denominator, we're doing something similar. We've got y sub I, so that's test score of student 1, test score of student 2, for example, minus, but here look what we're subtracting, y bar. That's the mean, right? It's the same for everyone because the mean is the mean is the mean. It doesn't differ by student, right? And that's why it does not have a subscript I. So I'm taking each individual student's score minus the mean, squaring it, and then adding student 2 minus the mean, squaring it, etc. So we're really doing a very simple calculation, but if we have a lot of data, you can imagine this would be a lot of work. So we just let the computer do it for us. But you see that it's not a super sophisticated equation, right? If we had to do this ourselves, we could, but we're not going to. Generally, we talk about larger R-square being better, right? Without any other trade-offs, we want larger to be better. So R-square of 0.85 is better than 0.23. However, it's important to understand low R-square is not always a problem. Please do not look at your regression results and go, oh my gosh, I have an R-square of 0.23. This is horrible. This model's junk. That is not necessarily true. It's important to understand that some fields of study are just harder to model, because there might be a larger amount of unexplained variation. And one example we deal with a lot in economics is trying to model human behavior. Because face it, guys, people are just harder to model. Now, where might we not see this problem? Something like sciences. There might be just more ability to better model certain scientific things. So, modeling people, much harder. There might be unobserved heterogeneity, things that we can't control for, that make it much harder to build a model that will be able to really accurately predict human behavior. A good model can show a lower R-squared. As I said, low R-squared doesn't mean our model is awful and we just throw it out. We can have a low R-squared in our model, but have several statistically significant variables, and I'll be able to show you some examples of that. And because we have very highly statistically significant results in a model, despite a low R-squared, we can still draw important conclusions from the results. So we don't just throw it all out because we have a low R-squared. R square is not the end all and be all. At the same time, we have to acknowledge that a high R square is not necessarily an indication that your model is good. And one reason for that is that R square increases with the number of explanatory variables that you have. In other words, the more variables you have in your model or you add to your model, the higher your R square is going to get. But more variables isn't necessarily good, right? So the higher R squared doesn't mean the model's better necessarily. And in fact, I could add random, unrelated variables and I could increase R square. If I was doing a model of student GPAs, I could add in all kinds of just unrelated things. And by chance, each of those variables that I've added, even though they're random, might capture just a little bit of variation just by chance, right? And if I do that for a whole bunch of them, my R square is going to go up. There are other reasons for high R squared as well. We're not going to go into that, but just understand that high R square, again, isn't the end all and be all. We can't look at a model and say, wow, high R square, I've done a really great job. That's not always true. For this reason, there's this additional statistic called the adjusted R square. Since more variables being added to a model increases R square, we can adjust for this using the adjusted R square. The adjusted R square basically penalizes the measure for additional variables. It's controlling for the number of variables that are in the model. Both statistics, the R square and the adjusted R square, should be reported. Let's look at an example. So I found this paper on decisions to pay dividends, basically the idea of frequency of dividends, and I want you to take a look at the R squares. There's two different models being presented, Model 1 and Model 2, and we don't need to go into what all of this is, but we do see that for Model 1, we have an R square of 0.303. In other words, Model 1 explains 30.3% of the variation. But look what's happening when we go to Model 2. We add two new variables. Now, that could improve the fit, but they're not highly significant. They're only significant at the 90% level of confidence, so that's not a strong result. But what happened to my R square? Our R square went from 0.303 to 0.321 because as we add variables to our model, R square goes up. Here's a study that I did with Professor Zirkle. We're modeling absences in a school. We're kind of investigating extreme absenteeism. And the first thing I want you to take a look at is all the dollar signs, not the dollar signs, what do you call those? The hashtags, the tic-tac-toe signs. Not even sure I know what it's called. But those are results that are significant at the 99.9% level. And we see a number of variables that are highly significant in explaining absences. And they're so significant that we can claim 99.9% confidence. And I see, just look at the OLS model. We don't need to worry about the second model, the random effects model. But look, I see 1, 2, 3, 4, 5, 6, 7, 8, or 7 variables and the constant, right? 7 variables that are highly, highly significant. But yet, look at the R squared here, 0.174. Well, there are probably a lot of variables that need to be controlled for that we don't have information because we're modeling human behavior, which can be very difficult and influenced by a whole lot of things, including, innate abilities that just are hard to measure. This model is an hourly wage model. Notice that we only have 2 explanatory variables, age and a dummy for if the employee is male. In this model, we do see a pretty low R squared, 0.06. Now, you might argue that this model is kind of bare bones, right? There's lots of things we could think about adding to hourly wage models besides just age and male that might have a lot of explanatory power. So in this case, you might say, okay, your R square is suffering from a pretty skimpy model. But what I do want to point out is the adjusted R squared. Now in this case, you do see that the adjusted R squared has a little bit of a penalty for having variables, right? So it kind of controls for the number of variables, but it's not a very big penalty here because there's only 2 explanatory variables. So the more variables we add, likely we're going to see a larger penalty in that adjusted R square. But the adjusted R square will always be less than the R square.